All right, this is my screen. This is FlexSim 2022, and I'm going to be talking about reinforcement learning. We're going to talk about this from a very high level. If you open up FlexSim 2022, it looks like this. And a great place to start talking about reinforcement learning is in the toolbox. If you add connectivity, there's now a reinforcement learning tool. So I'm going to add that to a model, and you get this user interface. So the things we're going to talk about today, we're going to talk about what's in this interface, what these things are, what they do, how they relate to reinforcement learning, what reinforcement learning is, stuff like that. And what FlexSim has provided in the realm of reinforcement learning in FlexSim 2022. So I'm going to start by pushing this little help button, which is going to bring up the docs.flexsim.com user manual page about reinforcement learning. So this page goes through and it talks about the various properties that are on this user interface. And we'll get there and we'll talk about those things after we talk about what reinforcement learning is and how it connects to FlexSim. So everything's kind of interrelated, and as we discuss stuff, we will make reference to the UI and the manual primarily. So the reinforcement learning tool enables you to configure your model to be an environment for reinforcement learning algorithms. What does that mean? What is an environment? And what's a reinforcement learning algorithm? So to talk about those things, we're going to head over to another section of the user manual that's linked right here called Key Concepts about Reinforcement Learning. So I'm going to click on this, and it's going to think for a second, and it's going to open this up. So in addition to the documentation about this user interface and this tool, there are 3 pages discussing reinforcement learning in the user manual for FlexSim 2022. And this page right here is an overview talking about what reinforcement learning is. And so we're going to talk about it. So reinforcement learning starts with an environment. You have some environment where an agent wants to make decisions. So for a simple example, an agent you could train an agent to learn how to navigate a maze to get to the end, right? And the maze is the environment. So the agent, when he takes an action in the environment, he moves a little bit, and then he can observe the environment, see what's going on, right? And that tells him the state of the environment. If he's perhaps standing at a dead end, it says, hey, you can't go forward anymore, right? And then he can choose to take an action like go left, go up, go right, go down, whatever. Eventually, right, he may make it to the end of the maze and we could give him a reward. So that is kind of the basic premise of how reinforcement learning works at a very, very high level. Is you have an environment where an agent's an algorithm, a computer algorithm that's going to make a decision, right? Lives in an environment where he knows stuff about the environment, the state of the environment. And when he makes actions, he can receive rewards based on the actions he's taken. Now, there may be a delay between when he takes an action and when he gets a reward. And reinforcement learning algorithms have been designed with that in mind, right? He may not get rewarded until he reaches the end of the maze, but he made good decisions along the way. And so there are various types of reinforcement learning algorithms out there. Okay, so if I click on this little link down here, it'll take us to a Wikipedia page about reinforcement learning. And there's all these various different types of reinforcement learning algorithms, and they have different types of action spaces and policies. And how they learn is a little different. but the general overview of what happens during a reinforcement learning episode is the same no matter which type of reinforcement learning algorithm you're using. And so for FlexSim, we implement just this top part, this environment part, and the actual agent lives somewhere else, okay, in a reinforcement learning algorithm that could be written in whatever programming language you want. There's been a lot of research done in reinforcement learning in Python, and the example here in the user manual uses Python to demonstrate how to train a reinforcement learning algorithm using FlexSim as the environment where it learns. So the agent starts by taking random actions, right? And there's a trade-off between the actions he takes where he's exploiting what he's learned versus exploring new possibilities. So as he takes random actions and starts getting rewards, then he'll start taking actions that are more optimized in order to maximize the reward he gets. And over time, running through a lot of training episodes, he will eventually learn how to take actions that maximize his reward. And that's the whole goal of this, is to teach a computer algorithm that based on a certain state, he should take this action to teach the computer how to make decisions that will lead to maximum reward. All right, so that's cool. That's the overview of what reinforcement learning is. What FlexSim 2022 has in it. Now you could always do this with FlexSim. You could connect to FlexSim from a reinforcement learning algorithm, and you could tell it to run, and you could, get observations and make actions. But what we've done in FlexSim 2022 is we've added a tool to make that easier. So you have a nice user interface, and you have a nice example in the user manual to walk you through doing that. And the example in the user manual uses these two Python packages. One of them is called Gym, OpenAIGym. And OpenAIGym is a Python package that's a toolkit for communicating with different types of environments, right? So they've got like this physics environment, and they've got this lunar lander environment, and a cart pole environment, and stuff like that. There are different environments, and an agent can communicate with those environments through a standard interface of there's certain methods. If you implement, we've got an Atari environment to teach using reinforcement learning, teach algorithms and train policies to interact in that environment. And so what we've provided in the documentation here is, if you click on this, it will download a zip file that has 3 Python scripts in it. And these scripts, one of them is a subclass of an OpenAIGym environment. So it implements all the methods needed used to communicate with FlexSim as a gym environment. So anything that trains with a gym environment, you can use that Python file to communicate with FlexSim. And then the other things in here is Stable Baselines 3 is another Python package that provides implementations of reinforcement learning algorithms. So I talked about there's these various different types of reinforcement learning algorithms, and each one, they follow the same basic structure of actions and observations in an environment, but the exact specifics of how they learn and how they account for different timing of rewards and how they store their action spaces and their state spaces is different. And Stable Baselines 3 is actually implementations of those. So it has these various types of reinforcement learning algorithms that you can use. And in the example in the user manual that we walk through, that it walks you through using Stable Baselines 3 PPO algorithm, which is right there, Proximal Policy Optimization, which is a pretty cool algorithm, and it supports a variety of different types of observation spaces and action spaces. So in the user manual, we've got these 3 files. So we downloaded them, and then it has instructions on how to configure Visual Studio Code to be an environment so that you can load these files in and run this Python code to communicate with FlexSim. And so the actual reinforcement learning algorithm is going to be executed in Python, where you create one of these things and you tell it to learn. And the model in Python uses an environment that is a FlexSim environment that communicates with the FlexSim program. And so what this does is it steps you through using Visual Studio Code to communicate, get these Python packages and communicate with FlexSim to do reinforcement learning. So you don't necessarily need to use Visual Studio Code. You could use Visual Studio or Anaconda or straight Python. You can really use whatever you want to do reinforcement learning. But this example, to keep things simple, uses Visual Studio Code, and it walks you through that with these example files. And you can take these files and you can look at them and see what they're doing, creating environments and stepping through the different processes of taking observations, taking actions, getting observations back, adding up rewards, etc. Yeah, so that's configuring an environment, and the user manual page here walks you through that. The next step is actually training on a reinforcement learning algorithm. So this documentation page steps you through that, building an example model of a source cube processor sink, where you have changeover times as item types shift, and it trains an algorithm to learn how to pick which item to process next in order to minimize the changeover times, in order to maximize the throughput of the system. And this purposefully uses a very simple model in order to focus on the reinforcement learning concepts. But it's still, it walks you through step by step building up this model so that you can use it. And so what are these things? Let's actually talk about some of these things. So observation space. I like to talk about observation and action spaces using the Q-learning example. So here's a nice picture. In Q-learning, you can imagine that you have a big table where each action you can do is along the top, like go south, go north, east, west, pick up, drop off, kind of like going through a maze, picking up cheese, taking it to the end or something like that. And then at any given point while you're doing that, you're in a certain state. So there's 500 states. And as it runs the algorithm, it will put rewards into these cells so that when you're in a given state, it can choose to maximize the reward. And it uses this formula that accounts for decisions that may have happened in the past, so it can learn over time and have delayed rewards. So an observation space is, these are the things that the algorithm knows about the system. Okay, for example, right, in a maze, it can know, hey, can I go up? Can I go left? Is that blocked? Right, things like that. Or where is certain stuff? Or what items, what was the last item type I processed? what item types are sitting in my queue right now, things like that. And when you define your observation space, so there are different types of observation spaces, and these different names of things like box, discrete, multi-discrete, multi-binary. These are names that come from this OpenAIGym interface. This is the names that they use to define these kinds of space. When you pick one, it will actually show you the parameters of that type that fit in that space. So a box space will show you whatever continuous parameters you have in your model. All right, so if I added a bunch of continuous ones, I can say, hey, I'm using these continuous parameters. And parameters are actually constrained variables that have bounds. And so it knows the upper and lower limit of what it can choose and try and learn about the space and those parameters. So action spaces are the same way as observation spaces. You have a set of, hey, what can I do? So I could have, say, an integer between 1 and 5. And then in my action space, I could pick that. And it's, hey, I can set this parameter to the values between 1 and 5. Those are the choices I can make. And those can map to whatever decisions your AI wants to make. For the maze example in that page, it was go up, go left, go right, etc. For the example in the user manual, right, there's 5 item types I can pick. And so this walks you through setting a parameter that is an integer between 1 and 5 of which item type should I pick next. So those are action and observation spaces. And the reinforcement learning algorithm first communicates with FlexSim and says, hey, what are your action and observation spaces? And FlexSim sends back, hey, this is what they are. And then it starts running the model, and it first makes an initial observation, and it will ask the model, hey, send back, these are the parameters. And the model will send back, hey, these are the current values of the parameters. And then based on that, the reinforcement learning algorithm will send, hey, I want to take this action. And then it will send that action to FlexSim, and it will run the model from there. And then the model, you set up decision events, and they work kind of like wait for event, where you can, sample, say, I want to make a decision based on the send to port, right? I want to pick where to send using my algorithm. And so whenever the processor has a send to port, right before that event happens, it will take an observation of the system. The reinforcement learning algorithm will send, hey, this is the action I want you to take, which will set the action space parameter. And then in that event, you can read that parameter and use it to make a decision in the simulation model. So this documentation walks you through an example of building a model that does all these things, right? It steps you through configuring parameters to be used in an observation space and an action space, setting up the decision events, and then filling out these triggers that we'll talk about now. So on observation trigger, normally you can just set your observation parameters willy-nilly while your model's running, right? Whatever your parameter is keeping track of the current state of the system, you can just set that parameter value. But there's a trigger that fires right before it takes an observation in case you want to set them explicitly. So you have this on observation trigger that will fire that lets you set your observation parameters whenever it is about to take an observation. And with an observation, it also has a reward function, which we showed in that little diagram. And the reward function returns just a number. It boils down to, this is a reward, and you can give a negative reward if you want to punish the algorithm for making bad decisions. You give a positive reward for making good decisions. And then you also pass whether it's done or not. And so the reward function actually controls when an episode is done. When you're training a reinforcement learning algorithm, he will make many decisions all along through the course of one model run. And then when the reward function says it's done, that will be the end of an episode. Like, hey, I got from the beginning of the maze to the end of the maze. That's one episode. Same thing with making decisions in a simulation model to train the algorithm. He can make lots of decisions about which item do I pull next. And then when I'm done learning, you pass that you're done in the reward function. And so with those steps, you can actually then train an algorithm. And this documentation steps you through doing that, running these Python scripts where you'd specify where FlexSim is, the name of the model, how many time steps you want to learn for, where you want to save the output of the trained policy to. And then you run it, and while it's processing, you'll see the algorithm start to learn and start to get better at making decisions. For example, here, the episode, after it had run 4,000 times in a few minutes, the episode, he was processing about 36 items. And then after training for 10,000 times, after 5 minutes or so, he was now processing 43 in the same amount of time. And so he had learned to make better decisions about which item to pull next by making choices and receiving rewards. And this explains that and walks you through doing it yourself and talks about how you can improve upon the algorithm and things that you can do. And the last step after you've trained a reinforcement learning algorithm is using it. And so the process of using a trained machine learning model to make a prediction is called inference. And so this documentation walks you through and has an example of an inference server. So after you have a trained model, you can host it as a web server, right? So that you can query it with HTTP queries in order to pass it an observation and receive back a prediction of what you should do, so that you can then implement that in a real live production environment. But you can also use it to verify and evaluate how your reinforcement learning algorithm works in the simulation. There's pick options in the on request action for querying the server or for taking random actions. And so you can see and evaluate, hey, how well does this algorithm perform by using this on request action trigger. So what this on request action trigger is, so if you're training and you fired FlexSim up via the Python script in order to train a reinforcement learning algorithm, then this on request action does nothing. Okay, you have this tool and you have this trigger and it does nothing. But when you run FlexSim normally, what this tool does is it does the same process, but instead of training the algorithm, it fires this trigger whenever the algorithm would have been making a decision. And so that gives you an opportunity to then make a decision yourself. So you could write custom code that is, right, some set of rules, some heuristics of what you want to do, or you can query a server and ask a trained algorithm what to do, or you could take random actions. You can do whatever you want the simulation to do at the moments where, when in training, that's what the AI would be telling it what to do. And so that's what this on request action trigger is for. And you can have multiple reinforcement learning objects in your model. So if you have different AIs making different decisions in different places, you can put those into your simulation model as multiple reinforcement learning objects. When you're training and it spawns up a FlexSim, it will use the very first one in the list as the reinforcement learning algorithm that is training at that time. And so if you want to train a different one, you just need to reorder them with the toolbox and then save your model. And so that is a very quick, high-level overview of what's in FlexSim 2020 with regards to reinforcement learning. It's these 4 documentation pages, these 3 Python scripts that show you an example of how to communicate with FlexSim, and this tool that knows how to handle all the various events and steps and data that a reinforcement learning algorithm needs.
Thank you, Phil. Hey, real quick, I do want to mention I did answer a question during Phil's presentation, and for those who are interested, OpenAIGym and Stable Baselines 3 are open source. I know that was asked. Looks like we do have a question pop up. Is an algorithm's learned knowledge written back into the algorithm itself, or is it stored externally?
Good question. So when you train it, after you're done training it, let me open up the code right here for training. So here in memory, using, this is how Stable Baselines 3 works. So you train up an algorithm, and depending on the algorithm, they have different parameters that you can use for how they'll learn. They're called hyperparameters. And then after it's trained, it will store the data in a certain way of, this is what I've learned, depending on the type of algorithm you've learned. But all of the algorithms implemented by Stable Baselines have a save function that will save that to a file. And this will just dump out a zip file, and you name it here. And that data is, you don't, at that point, you no longer need the FlexSim connection. You can just have that chunk of data in that zip file. And that's what this inference server uses. It loads up that zip file, and it walks you through this in the documentation. It loads up that zip file of, this is the data. So I trained this algorithm and it needed 137 kilobytes of data in order to make predictions based on observations in the state. So you load that up, and then you can execute it. So you can say, you can pass it an observation to predict an action, and it will come back. It's really 2 lines of code is the actual reinforcement learning stuff here. There was a question about how much coding knowledge is required. So to actually use this, you don't really need any coding knowledge. It steps you through exactly, hey, these are the lines of code that you could change. But since it's using these standard packages in Python, if you want to adjust and change these example code, you're welcome to go and change it and do whatever you want. But the user manual actually walks you through exactly, hey, these are the lines where something interesting is happening that you should fill in the code if you're using these things. And it's basically paths to FlexSim and paths to the model.
Hey, Phil, in the interest of time, because we have about 3 questions outstanding, would you be able to answer those just through text while we set up the next presentation? Perfect. So just look for the answers to those questions in the Q&A area. And thank you very much, Phil.